All right, I'll have to get some water here. I've been waiting to use this mug for God knows how long. Okay, welcome back to the second video of this week, week 1 of this course, Physics 325 Optics. And what we're doing right now is we're trying to understand optics in terms of electromagnetism. And in order to do that, we have got to study the fundamental equations of electromagnetism. And here they are. These are Maxwell's equations. Now, as you notice, there's some funny symbols in here, upside down triangles, crosses, and dots. And that's why we devoted the last lecture, the last video, to understanding what these symbols were and how to work with them a bit. And we're now well equipped to understand what these equations are physically telling us. Now, I should say, first of all, that it's a very good thing that we've invented these funny symbols and this formalism. This is not the way that Maxwell's equations originally looked. In fact, there were 20 of them. And these are really the same thing, except the mathematical formalism was not sufficiently developed to write them succinctly like this. So you can thank vector calculus for being able to write this instead of that and memorize 4 equations instead of 20. But really they're the same content. Okay, so we're going to work with this nice succinct formalism to understand how electromagnetism predicts optics. So let's get started in just seeing what these equations really tell us. The first one is called Gauss's Law. So Gauss's Law, what is it actually telling us here? It says the divergence of the electric field is rho, the charge density, over a constant, the permittivity of free space. We'll get back to that at the end of the lecture, but what is this rho here? It's the charge per unit volume. So let's take a very, very, very small volume and look at how much charge is in it divided by that volume. That's what we're going to call rho, okay? And epsilon is just a constant, permittivity of free space, 8.85 ... times 10 to the minus 12 farads per meter. Don't worry so much about that right now. This is the important thing. It tells us that the divergence of the electric field at a point is equal to really what's the charge contained in that point. Okay? So let's remember what the condition for a non-zero divergence was. All right? A non-zero divergence meant that we had more lines exiting than entering a small region, or vice versa. We had this animation last time. Whoops. Let's run that again. And that's what it told us, right? So this is a non-zero positive divergence. Non-zero negative divergence had a bunch of lines going in. And a zero divergence meant that there was as many lines going in as out. Okay? So what is this really telling us? It tells us that the charge is the source of electric fields, right? If I have to have a non-zero divergence, I have to have more lines going out than in, or vice versa. And that tells us that we need a charge. We need charge to create a field. And look at the form of this. This is a divergence. This is kind of normal. This is radially pointing outward. So it really tells us, kind of in quotations, that it's a source not only of electric fields, but electric fields that move away from it. Okay? We can get more formally into that, but that's really a course in electromagnetism. For now, let's just note this fact, this neat fact that Maxwell's equations tell us that charge is what creates these radially outward electric fields. We have a very similar equation here. Sometimes you just call it Gauss's other law, or Gauss's law for magnetic fields. It tells us the divergence of the magnetic field is 0 always. Why? Well, really what that says is that there are no things in nature that make a magnetic field that looks like this. We can't have a magnetic field pointing outward. There are plenty of things that make a magnetic field that might look something like this, that have lines going out in different directions, or vice versa, right? But there are no charges in the same sense that create magnetic fields. So there's no magnetic charges. Sometimes you call this magnetic monopoles. This is what a magnetic monopole would look like. It would look like a charge does, but for magnetic fields. There are magnetic dipoles that have 0 divergence, as many lines going in as out, but there are no magnetic monopoles like this. Okay, so that's what the second of Maxwell's equations tells us. 2 down, 2 to go. Let's go to the third. This is known as Faradays Law, and it tells us something interesting. Let's just read the equation. It says that if I have a changing magnetic field, okay, I create an electric field. So I take a magnet and I spin it around, or I move it, or I wiggle it, that's going to create an electric field, and more electric field the faster I'm moving it. Okay? So a changing magnetic field is a source of electric field. Now let's look at the form. This is not the divergence of E, it's the curl of E. And curl is kind of transverse. So this is kind of giving us a sense. This is very hand wavy, but it's giving us, when we create a field, a magnetic field which is changing in this direction, we're creating an electric field which is kind of curling around it. So it tells us that it's kind of a rotational field. This is what we have so far, is that we can have static charges that are just sitting there in space. That creates electric fields. We have a wiggling magnet, a changing magnetic field. That creates a different type of electric field. So how do magnetic fields ever get there? Well, that's our fourth Maxwell equation, Amperes Law. Okay, and this tells us two things. The first thing it tells us is that, well, if I have an electric field and I wiggle it around, for example, a charged plate, for example, I'm moving that around, that's going to create a magnetic field. And the faster I move it, the more magnetic field I'm creating. And it's rotational in the same sense that it was for the electric field. Okay, so a changing electric field is going to be a source of magnetic field. But there is another term here. Okay, what is that J? J is called the current density. And if I have a bunch of charges that are moving, right, charge dq by dt, that is what we call current, right? Charge per unit time. But usually in like electronics, for example, we're talking about current moving in one dimension through a wire. So imagine we took a small area and we took the limit as that area goes to 0. So we're taking like, we're really like zeroing in on one direction in space, and looked at the charge flowing through it, kind of normal to the surface of the current through that surface. We'll call it I perp divided by A. That's what my current density is. Now it has a direction, right? So it's a vector, but it's really the current density, the current per unit area. And this tells us that while we had charge, which created electric fields, it's the source of electric fields, we have current, which is the source of magnetic fields. So magnetic fields are created by currents or changing electric fields. Electric fields are created by charges and changing magnetic fields. This is very interesting in the sense that somewhere, somehow, there had to be some charges that created them. But imagine we're just off in the middle of free space, right? And there's no charges, no currents anywhere. We can still have interesting things happening. So we look at Maxwell's equations in a vacuum or in free space. Now, there's zero divergences, there's no sources, but the curls are not zero, right? So if we have a changing magnetic field, that's going to create an electric field. A changing electric field will be creating a magnetic field. And this is kind of an interesting interplay. This actually is very important. It leads to a picture of what is going on with electromagnetism. Okay, so let's think about this. Changing electric field creates a magnetic field. Changing magnetic field creates an electric field. And that can kind of cycle. Notice that these terms have opposite sides too. Okay, so imagine if somehow, just somehow, I have a magnetic field which is ramping up. That's going to create an electric field, and as that electric field starts ramping up, that's going to pull the magnetic field down. The rate of change is going to be negative to the electric field, and it's going to pull it back down, right? But that pulling it back down is going to pull the electric field down the other way, and they're going to be basically pulling themselves up and down and back and forth, wiggling and dancing through space. And this is kind of a hint that we can have something called electromagnetic radiation. We create a little wiggle. That wiggle creates an electric field, that creates a magnetic field and pulls back the electric field, that pulls down the magnetic field, and it just moves on propagating through space. That is what's going on with this, the photons, or the electric field rather, in this laser pointer here. Okay, that's where we're going. And it's all contained in Maxwell's equations. So that was very literally hand wavy. Let's be a bit more rigorous, okay? So we're gonna play with Maxwell's equations a bit more. We now know what they mean. Let's think about Maxwell's equations in free space, and we'll apply one more thing from last video. We'll apply this vector identity. The curl of a curl is equal to the divergence of the gradient of the divergence minus the Laplacian, right? So that's written here. This is true for any function. And let's apply it to a specific function. Let's apply it to an electric field. For now, we'll work in free space. Okay, so we'll apply it to the electric field, and we have a fact from Maxwell's equations that the divergence is 0 out in free space, right? So even if there's no charges anywhere, I still have this relation that the curl of the electric field is equal to the Laplacian of that field at a given time. Okay? Quite interesting. That kind of constrains the form that the electric field can take. But we can do more. Let's look at this equation in a different way, and we'll plug in some more of Maxwell's equations. Notice that curl of E in the middle there. Well, we know that from Maxwell's equations from Faradays Law, that the curl of E is the negative partial time derivative of the magnetic field. Okay? So we can just plug that in there, and this is what we get. The curl of E is equal to either the negative Laplacian or the curl of the negative derivative of the magnetic field. Okay, now all these things are just derivatives. Derivatives are nice. They're all, you can kind of move them around. Differentiation is a linear operation, and it behaves very nicely. So the curl, remember, is just dx's and dy's and del z's or dz's. So I can do this, d by dx of df, whatever my f is, by dt, or I can do d by dt of df by dx. Right? I can do it in any order. I can move the things around. I can also move the negative sign around. So let's just do that. We're going to pull the partial derivative and the negative sign out, and we get negative d by dt of the curl of the magnetic field. Right? We're not done. This is great. There's a Maxwell equation for that. We also know the curl of the magnetic field, right? It's this mu naught epsilon naught times the time derivative, partial time derivative of the electric field. Okay, that's Amperes Law. So we'll plug that into those brackets, and this is what we get. We'll apply the same trick that we had before, right? This is nothing but just plugging in equations, and now we're going to pull everything out. So we have a different way of writing the curl of E. There's two equivalent ways of writing it. The curl of the E is equal to negative the Laplacian of E, and it's also, by Maxwell's equations, equal to negative epsilon naught mu naught times the second partial time derivative of E. All right? They're the same thing, so we might as well equate them, and we can write this as follows. The Laplacian of E minus the constant times second partial time derivative of E. This is the equation we get. This, as it turns out, is a very important equation. This is known as the 3D wave equation, and this is all we need to predict electromagnetic waves. Okay, you may not be familiar. This may not be a giant epiphany to you, especially if you haven't worked with 3D wave equations, because they can be quite complicated. So let's actually just start baby steps, and we'll start with the 1D wave equation. Okay, let's write this exact same thing. How do we do it in 1D? Effectively, what we're going to do is we're going to take the gradient. We'll say it moves along one direction, z, and we'll replace things like the gradient with the second direction in one dimension. Okay, so let's look at f of z and t. Okay, so one-dimensional wave equation. I claim the following, that in order to solve this one-dimensional wave equation, I'll write it up here, I have to have a very specific relation between space and time. So here's my wave equation, d2f by dz2 minus d2f by dt2, and I forgot an important constant in here, 1 over v squared. We'll see what that is in a second, equals 0. All right, I'm going to snap my fingers and make this neater. Okay, so that is the one-dimensional wave equation, and my claim is that the special relation between space and time is that I have to have really, this is a function of two variables, it really has to be a function of one variable, such that this is equal to f of z minus vt. All right, this is a one-dimensional, this is one variable, right? So just to see that, let's let gamma equal z minus vt. If I know z, I know t. So this is really equal to f of gamma, one variable only. Okay, so let's prove that. Let's prove that if I have this function here, then I automatically save this one-dimensional wave equation. I solve it. So how are we going to do this? So let's look at df by dz. Well, from our our chain rule, we have df by d gamma times d gamma by dz. What is that? Grab another color here. d gamma by dz is just equal to d by dz. I'm running out of ink here. dz minus vt, that's equal to 1. Very easy derivative. So this is just equal to df by d gamma. And similarly, I do that again, d2f by dz2 is equal to d2f by d gamma 2. Easy enough. How about the other one, the other variable? So let's look at df by dt. df by dt is equal to df by d gamma times d gamma by dt. And d gamma by dt, it's a bit more interesting. D gamma, oh, we're just using the last few little bits of ink here. D gamma by dt is equal to negative v. Negative v, that's it. Negative v. All right. Equals negative v times df by d gamma. All right. So last but not least, d2f by dt2, let's get another negative v out here, is v squared d2f by d gamma squared. Okay? So if my function is of the form f of z minus vt, I automatically, for free, get that d2f by dz is equal to 1 over v squared times d2f by d gamma squared, right? 1 over v squared, times dt squared. All right, this just falls out, directly out of the math here, right? This is actually just to write it explicitly. One side is d2, I think this one's gone. Let's thank it for its service. And write this in monochrome now. This is actually just going to be d2f by dz squared is actually d2f by d gamma squared, and 1 over v squared times v squared d2f by d gamma squared. So these things are automatically satisfied. Okay, just a quick little derivation. So any function of this form is going to solve that one-dimensional wave equation. All right? What does that actually mean, by the way? This is actually a plus or minus z or t because v can be positive or negative. But what does this actually mean? If I have a function, f of x, and I take it, or f of z rather, and I go f of z minus something, that's going to shift the something to the right. F of z plus something, it's going to shift that something to the left. Okay, so this is just describing something that moves linearly with time in one direction. So this is f of z here, and let's just look at f of z minus t for various t. This is what it's going to do. It's going to propagate linear this way. So that's great. There it is. So this is what it's going to do. It just propagates linearly with time. Do you see that? Okay, and we don't have to have some, this is just some arbitrary function. It was like a Gaussian times a sine times a polynomial. I just made something up. We can have a simpler thing. We can have, for example, a sinusoidal wave and plug that into this wave equation. In this case, I better actually say what I've written there to make things a bit more clear. Here, we're just plotting, literally what I plugged into Python to make this is cosine of, I think I wrote 2 z minus vt, and I animated it for different t here. And that's what this wave is actually doing over various times. Okay, so that's the one-dimensional wave equation. And let's compare those now. We have the three-dimensional and the one-dimensional wave equation, and we can immediately see something here, that they're of the same form, but here we have 1 over v squared is equal to epsilon naught mu naught, so that v squared is equal to 1 over epsilon naught mu naught, or v is equal to the square root of that. Okay? So the Maxwell's equations predict a wave equation that has a very particular velocity. A very particular velocity is 1 over the square root of epsilon naught mu naught. And these have numbers. They're fundamental constants of nature we can look up. Epsilon naught is 8.85 ... picofarads per meter. Mu naught is about 1.25 microhenry per meter. These are just things that we can measure, and we multiply them, take the square root, take 1 over that, and we get some number out. Let's do that. Feel free to pull out your calculators. I've done it, and this is the number we get. Exactly, by the way. We get exactly this number. C, which we call the speed of light, which is 299,792,458 meters per second, 0.0. This is actually defined this way. Everything else is kind of defined around C. And this is a fundamental constant of nature. So remember, we're talking about this. We wiggle an electric field. That's going to cause a magnetic field. And this electromagnetic field is just, this dance is going to occur through space. It's going to propagate out at a very particular speed governed by Maxwell's equations, which is about 3 times 10 to the 8 meters per second. It is this value exactly. This comes directly, fundamentally, out of Maxwell's equations. So that's it for this lecture. This is the interpretation of Maxwell's equations and how we get waves out of them. Let's summarize. So the first thing is that, the very first thing we came across is that Maxwell's equations tell us about the origin of electromagnetic fields. Charges or changing magnetic fields are what create electric fields. Currents or changing electric fields are what cause magnetic fields to come into existence. Okay? And we can apply a vector identity, do a bit of calculations, and we wind up with a wave equation, even in free space. Even if there's no charges and there's no stuff, we can still have electromagnetic waves which are going to propagate through space. If there is stuff, we get a modified wave equation. We'll get to that in a few weeks, but it's still a wave equation. Turns out if it's going through something like glass, it goes about 1.5 times slower, but you still get the same form. Very neat stuff, and we are already really equipped to understand that. Finally, if we actually look at the form of these solutions and compare to a one-dimensional wave equation, we see that these waves propagate at a very particular speed, about 3 times 10 to the 8 meters per second, and which is a constant of nature, which we know now is the speed of light. All right, so that's this lecture. Next lecture, we're going to go into a very particular solution of these. We've kind of stated the three-dimensional wave equation. Let's actually look at some solutions of it, and we're going to look at kind of the most important solution to the wave equation, because we can use it to build all other solutions, and it's called the plane wave. But that will be next time, and I will see you then.